Okay, so yeah, I'll be discussing the documenting and providing AI services for the HPC community. Later on, I'll focus specifically on providing AI for numerical weather prediction type workflows for specifically for NSF NCAR, but wanted to first touch on documentation that currently exists at large across the community, at least a current rough assessment of which. So various HPC sites, and I imagine most of us work in kind of either a computing center of some sorts that provides computing services to your community. Many sites have varying levels of types of documentation to provide to their users. Some are more in depth, some are more superfluous, and maybe point to, say, specific documentation for a specific tool that might be commonly used. But oftentimes, especially in the HPC space, you might require, say, specific, workflows that need to be shown and described in order to facilitate, exact like usage needs of, say, a particular tool, given the way in which MPI or your GitHub node, your GPU nodes or the fabric across your system is set up so that these various tools can be used effectively on these systems. So, for example, if I click on this NERSC one here, they actually deploy like a TensorFlow module. I'm not sure. I'm pretty confident that not every HPC site provides like, specific AI software optimized for their systems, but nonetheless, this is what a model that NERSC does. But they actually go through and detail how to like use that particular module environment, as well as say some container environments that they encourage the user community to interact with. One of the notable things, at least I know of, and is important to me as an NSF NCAR person who maintains our cluster. We're also very similar to NERSC, and one of the main hurdles in terms of many of our HPC users that want to have an optimal usage of their AI workflows with, say, TensorFlow, is how well it's integrated with Nickel. That's the NVIDIA Collective Communication Library, which offers a more optimized like communication path between GPUs when you're in multi-node configurations of larger AI models. But getting that set up for most common users is pretty difficult. So having pages like this that document and make clear pointers to, say, tools that make sure that integration is done correctly is important. And it goes beyond just say, pointing people to the existence of TensorFlow. So that if anything, I'm just highlighting through showcasing this that there are varying examples, at least in this case, of TensorFlow, but certainly many other types of focus tools that are like put out there to that people tend to document and showcase for their users, whether it's like general AI workflows or deep learning examples that can include like Horovod or as well as like PyTorch and TensorFlow. JAX is also commonly cited. This is not a comprehensive list here, but nonetheless, one complicated tool I know a lot of people use is often TensorBoard because that often requires a open port that's need to be made available on either external to the cluster to like interface with, say, a TensorBoard interface, or otherwise making it internalized and doing some sort of screen share type option or remote desktop configuration to interact with a TensorBoard display. Um, Beyond, say, some of these tools, there's also like, how to use like MLflow or Hugging Face within the context of some systems. And one of the more kind of like, I think, building areas of support or documentation that I'm seeing pop up at places is LLM or inference endpoints and how that's provisioned and provided to the community. So, that can have varying names of how that's actually done, whether that's like an on-site chatbot and how that's configured and loadable within a module or some other software ecosystem that's provided to users. But nonetheless, there's a growing array of options in how people provide these resources to folks. And I think it's important for whatever tools that your site chooses to make available to your users, to strongly consider how well you document the usage of those resources to your community, such that they can be effectively, utilized and also ideally optimally utilized. Say an example of how I was pointing to TensorFlow's usage on like nurse systems as well as NCARs. And if it's incorrectly configured with, say, not appropriately set environment variables or nickel not integrated correctly into the software build system, then you might have a model that runs 50% slower, sometimes even worse, depending on the configurations that the default options of like say TensorFlow and stuff in Conda does. Um, so you know I'd be happy. I believe through the working group, there's a more comprehensive list of some of these types of like already existing materials out there that help facilitate these type of usage. But it's interesting at least to see to do this kind of like rough survey of what broadly is available that you can find easily online and what's available to the public. Um, but as an example that I wanted to focus on in terms of like something I've been working on documenting better for our community is this AI for numerical weather prediction modeling efforts and workflows. So, AI, obviously has many different applications beyond LLMs, one of which in the Earth system science community is generative models for weather forecasting, whether it's, short-term weather or medium to long-term weather or climate. There's a growing community in that space to do a lot of that work. So for example, in the AI space, there's you typically have these like forecast steps that be done in time, and that's usually what's currently done with at least being researched and actually done very well with machine learning. There are other pieces of that workflow that's not done with machine learning quite yet, or at least in a integrated fashion. Namely being data simulation, where say at each time step you'd have like new observations coming in from on the ground sensors or satellite sensors, and that would then be simulated or through a data simulation process as it's known to put back into the model. And then you do the next forecast step or where and essentially throughout that kind of workflow. So there's a if you'd like, there's a link here for a talk kind of like highlighting some of these like recent advancements and weather forecasting using artificial intelligence. But there's plenty of models out there already, namely like AIFS, GraphCast Aurora from Microsoft, ForecastNet from NVIDIA, and CDIF also from NVIDIA. I'll say GraphCast was from Google, and AIFS is from ECMWF in the UK. And so, there's a building community out there to work on and analyzing and assessing the validity of these types of models. And so, but part of it is also like instilling a lot of trust in these models. Nonetheless, some of the results, at least for GraphCast, I'm highlighting the bottom right here. Um, there is already showing some like skillfulness in many of these models, and perhaps even greater skillfulness compared to more physics-based models only. Um, Nonetheless, there still exists a lot of hesitancy from the traditional Earth system science community and NWP community towards adoption and utilization of these tools. So some of the efforts in terms of what I'm highlighting here next is just the point that we want to make some of these more tools more accessible and at least like usable by a broader community of folks, so they can more easily interact with and actually assess and develop their own extensions to and validate the results of many of these models, so they can understand the differences that they exist between the physics-based models and the AI-based models. And so, and some of the ways to enable that access, there are already there are actually some building communities of tools around how workflow ecosystems are being built to assist that process. So a couple main ones are Earth-2 Studio, provided by NVIDIA, and that's actually a inference-based workflow engine that provides built-in workflows for prognostic, diagnostic, and integration of data sources and I/O and statistical operators for working with AI-based weather forecasting. Um, there's additionally the Anomoi framework, which also has recently been a higher priority within the NOAA ecosystem in terms of working with ECMWF and how that is being developed and deployed. The notable addition from Anomoi is it focuses additionally on the actual training step as well of many of these models to help facilitate research and developing better training pipelines and facilitating that process for more researchers, specifically in the AI forecasting kind of model development. Here at NSF NCAR, there's also the credit model, which is more of a community develop focused model and software platform for training and deploying AI models similarly as well to NMOI. And so offering a competitive alternative to the ECMWF based model based in Europe in terms of our own ecosystem of US based AI modeling efforts in weather forecasting. Um, Across these resources, the emphasis is at least that they are all open access. So we're focusing on open access at least in terms of how they're developed and maintained. In terms of we want to make sure we reduce the uh, anything that's not open access will reduce the ability for many people and organizations to engage or contribute. So with the advent of AI for many of these models, you might say with a larger physics-based model, it uses a traditional supercomputer to even like get a reasonable forecast that's usable for modern needs. But with with GPU computing and in an inference-only mode for many of these models, you might only need one GPU or a CPU if patient to only do the inference component if you're only interested in the results. So by making many of these models open access, it broadens the accessibility of these tools to the broader community outside of HPC. And so there's intentional efforts in terms of how we provision and provide these ecosystems, such that as when researchers engage with them, they continue to think about the ways in which that these software paradigms are providing for a future that democratizes access to many of these AI-based forecasting services, for example. So there's various efforts in terms of enabling that, such as through the GDEX platform at NCARF. It's a geoscience data exchange and making like AI-ready data that might be ingested into some of these models, as well as this the FAR RCN kind of program. I believe they have a workshop coming up in April, if you're interested, to that talks about the fair and AI readiness and reproducibility. And so many of these types of organizations and projects are moving towards these open access models of how AI-based NWP workloads are provided, as well as other applications as well. So an example of what I'll showcase in a bit is basically some of this work was extending this machine learning boot camp that we did to upscale some of our user community on some of these tools. We plan to also further this with a more publicly available educational module provided in the UCAR Comet program. It's a community meteorological training program that NCAR provides. Some of the existing catalogs that offer training resources I also link below, specifically the ML Bootcamp tutorial is a GitHub at the top there, as well as which I'll go through in a little bit, some of these Earth-2 Studio examples, and then below that is the NOAA Epic, which Epic is their one of their AI project teams within NOAA, and they went through some examples running NMOI. And then there's also other machine AI training platforms for through AI2ES. That's the artificial intelligence, trustworthy artificial intelligence and Earth System Science organization. So there's a collection of resources there for engaging with some of these kind of like learning materials and how a research community might engage in specifically Earth System Sciences use cases of this. So in our case, I have on the right here, the side of the screen, the various models that kind of already exists within AI for NWP. I mentioned, there's AIFS and Aurora, but there's also like Pangu, Stormcast, SFNO. That's essentially a spherical forecast net operator. That's the forecast net version 3, DLAS SIM. There's also varying data sources you could select, but all these are pre-configured within this Earth-2 Studio kind of environment. And so at least within NCAR, we have provided a Earth-2 Studio JupyterHub kernel that's like, clickable and selectable within our JupyterHub platform people can log into. And so when you say do that interaction and load up that model, you basically would just like import your required variables and classes from the Earth-2 Studio package. And you specify that you're using the forecast.net model here, or and then say you want to do a precipitation analysis using a diagnostic package that's provided and configured by the AI for NWP community within Earth-2 Studio. You might specify the GFS data source, and then you want to use an IO backend using ZAR. And so doing that, you can basically just run that model with like a run diagnostic and a few those input variables of what you set. It'll automatically run that inference, and you get like an output immediately within like a couple minutes, which is kind of inconceivable compared to traditional physics-based forecasts. But nonetheless, this sort of like pre-provided like training environment and use environment for like Earth Studio is already provided for our users. And we're working to improve the documentation of that resource for general folks to be able to explore and interact with and learn more about these types of interactions. So I might like at least like briefly like jump over to for an example of like how this kind of like looks as like a notebook, for example. We had a kind of a training event. We kind of like talked about, at least the history of numerical weather prediction. This is like the notebook where we kind of like ran this information, providing like interactive notebooks for some use cases or specific use cases that are valuable to the community can be, I think, really effective in encouraging greater interactivity and learning outcomes from some of these types of tools, especially when folks can go in and then change the code themselves. But we kind of just started with a kind of like background theory and understanding of kind of what's going on in terms of like the discussion of like the actual lecture portion. Um, but the second half of the notebook basically focuses on actually running the code and talks about the requirements of what's run. Where you would actually say load up the environment. In this case, it's already pre-installed for users at NSF NCAR. So this we already have Studio set up. But if folks wanted to set up or manage themselves, briefly describe how to do that. Um, Beyond that, you would actually have some examples of how to like run and use the model. So when we go down here, here's like the actual like example for running this kind of like code that I showed earlier. You just kind of like set up these environments, those specific backends you're choosing to use for this precipitation example I'm planning to run. Here's like a little like a class definition kind of like section here to highlight what's actually needed when you run your diagnostic model. Those are like the inputs needed that we set up in the previous step. And then here we actually then run that model and kind of I showcased those like screenshots before, so I'll just kind of instead of running it again live, I'll just show it here. But nonetheless, this kind of like first half the notebook runs within 2 to 3 minutes in terms of just getting through this large scale kind of like prediction here. But nonetheless, it provides like an actual kind of like workflow that folks can like interact with and see how it's actually done. So this final step is just getting the data from the inference that was done before and then displaying it in a way that's interpretable by someone wanting to understand the results of that forecast. There's a second half here that I would have showed otherwise live, but I think our H100s on our system are currently busy, and this requires a higher memory GPU node to run. But nonetheless, this would run a super resolution example of various like inference time steps, at 6 hour intervals of a global forecast. And again, this sort of model again only requires I think this one requires 4 minutes of time to run, but nonetheless, it's exciting examples to at least provide these like easy to interact with and interface kind of like projects for people to learn about and understand their needs within the community. So, in any case, those are some of the examples I wanted to showcase today in terms of how at least at NCAR we're like documenting some of these documenting and providing training services on some of these tools that are important to the Earth system science community. But I hope at least in terms of introducing the topic, in terms of also focusing on some of the other types of commonly documented kind of like tools across HPC clusters and data centers, that might at least instigate a discussion here in terms of like you know what what uh, what research workflows and AI needs do you think need to be better documented and provided for your own community? And are there inspirations of peer sites that you would like to utilize or recommend here to encourage others to perhaps improve upon or offer specific and tailored for your site that you'd like to share with the group? So that's kind of like my final questions as I kind of like wrap up here, just to you know think about like what, I would like to know from our community, what AI workflows are not being well explained or communicated or provided resources for within each of our HPC sites, and like to learn more how we can do that better as a community at large. So thank you for your time and happy to take any questions, and we can open up to broader discussion. I'll stop the recording, but